Hello. So in this problem we have a satellite in orbit, like that, of something like a planet, mass m, and we know the orbital radius is r. So we want to find out the period, the kinetic energy, the angular momentum, and the speed, so the magnitude of velocity, how they depend on r. So, for example, is t dependent on r squared or r cubed? And so our answer will be r to the power of something. That'll be our answer for each one. But really, let's just find the expression for period, kinetic energy, angular momentum, and velocity, and then they'll have an r in them, and our answer will be clear. So let's get started. I feel like v is the easiest one to start with. Looking at the picture here, I've already put v on it. It's clearly right there. And so we did one like this before. We can figure out how fast it will need to go to orbit up there. From a free body diagram on the satellite, there's a force of gravity pointing straight toward the center of the circle this way. And, yep, if we do the sum of the forces in that direction, we know that it has to equal mass times acceleration, but it's a special acceleration. It's going in a circle, so it's centripetal acceleration, and that's equal to the force of gravity. Is the only force in that direction. And so recall that centripetal acceleration is v squared over r, which is equal to the force of gravity, which is by Newton's law of gravitation, gm big M over r squared. Now notice I've introduced the variable little m. That would be the mass of the satellite. Now I don't know that, but I have faith that it's going to cancel out. Oh look, it did. Okay, now this r is the radius of the circle that you're going in. This r is the distance from the centers of the two masses, and in fact they are the same. Okay. And so it looks like v is equal to the square root of gm over r, or one could write this as gm over r to the power of 1/2. Once more, rewriting, we could write it as gm to the 1/2 times r to the negative 1/2. So, velocity is proportional to r to the negative 1/2. So that is the answer to part of our problem. Okay, so what to next? Well, period. We actually could write centripetal acceleration in terms of period right off the bat. I don't have it memorized myself. So let's see if we can figure out what the period is based on the velocity expression. We should be able to. Move down here a bit. So the period is how long it takes to get around my orbital path once. I know I'm going v the whole time, and I go all the way around. I get back, and that takes a time of t. Alright, well, we know from the definition of velocity we can write that v is equal to some distance, shall I say d for a moment, over time. In this case, the time we're talking about is 1 period. And what is the distance that we moved in 1 period? Well, that would be 2 pi r, wouldn't it? The circumference of a circle. We went around the circle once. Alright. And so what I'm getting here is that t is equal to 2 pi r over v, and I know what v is, so t is equal to 2 pi r over gm over r to the 1/2. Rewriting this a bit, we're getting 2 pi r times, let's see, r to the 1/2 over gm to the 1/2. Okay, r times r to the 1/2 is equal to, let's see, that's r to the, we're multiplying, and so we're going to add these exponents together. This is the same as r to the 2/2, and so it ends up being r to the 3/2 there, times 1 over gm to the 1/2. Okay, so it looks like t is proportional to r to the 3/2. Another thing we wanted to find is, how is kinetic energy proportional to the radius? We're moving at v, right? And we mentioned that there's this force of gravity, which is going to end up equaling the centripetal force. So mv squared over r is equal to gmm over r squared, right? So now, as I'm canceling, I want to keep in mind that I'm trying to get kinetic energy. Look over here, I've got mv squared. Remember, kinetic energy is 1/2 mv squared. I know there's an r involved, but maybe I can force this to be kinetic energy. Well, this r doesn't need to be here, so I'm going to cancel an r. I'm not going to cancel that little m. I know it's tempting, though. So, I'm also going to multiply both sides by 1/2. Why? I don't know, because I'm allowed to, as long as I do it to both sides. So this says 1/2 mv squared. That is kinetic energy. And it's equal to gmm over 2r. So that is the kinetic energy of an object in orbit. And we have a little m in there, but I suppose that's okay, because really we're just looking for how these things are proportional to r. And so it looks like k is proportional to r to the -1, right? 1 over r, or r to the -1. There we go. All right, and lastly, we're looking for, how is angular momentum proportional to r? So angular momentum is one of these things that for some reason or other we don't do that often. So let's just recall that it is equal, it is an L, angular momentum, and it's equal to I omega. It's probably the best way to go about this. This is the moment of inertia of the object about what it's rotating, and this is its angular speed of rotation. All right, so I've drawn this like 10 times. So it's got a speed v, but we can also talk about its big M in the middle there, it's shrinking. We can also talk about its angular speed, omega, right? Now we can get from v to omega pretty easily, and then, I mean, we've got our answer from before, but, oh, I don't know, let's start over once more. We know that the centripetal force is equal to gravity, like I did twice before, and it is MAC is equal to GMM over r squared. This is still r. But this time, let's write a centripetal acceleration differently. We can also write it as omega squared r. If you don't believe me, here is why AC is equal to omega squared r. I'm getting toward the angular velocity here, omega, but what I want is angular momentum, so we'll keep that in mind. First I'll go ahead and not cancel one of these. I'm going to divide over this r, and I'll get that, and I'll cancel an m. I'll get omega squared equals gm over r cubed, like that. And so omega is equal to the square root of gm over cubed. So the I of this thing, if we assume that it's a pretty small mass compared to the other mass and everything with the distances that are going on, we could just consider it a point mass, and the moment of inertia of a point mass is just mr squared, like that. And so L is equal to I omega, which is equal to mr squared for the I times square root of gm over r cubed for the omega. So now we need to combine these r's. It could just be a little bit messy, I suppose. Let's see. So this L is equal to mr squared times gm to the 1/2 over r to the 3/2, right? It's cubed, and then we took the square root. And we've got to do our algebra here. So this is the same thing as to the 4/2, right? This r squared on top, and we're dividing by 3/2, and so we end up that with L is equal to m gm times r to the 1/2. Okay, so the r could be inside there. Right, because we had 4/2 divided by 3, r to the 4/2 divided by r to the 3/2 makes r to the 1/2. And so L is proportional to r to the 1/2 power. All right, so that's about it. I went about a few of these just in, I did more work than I had to, basically, right? But it's good practice. Once we knew V up here, though, really, we know, so we did it for kinetic for period here. We just figured out what period is with respect to V, plugged in what we knew about V. Here we sort of started over, but we could have just noted the fact that kinetic energy is 1/2 mv squared and plugged in V. Okay. And that is about it. Thank you.